In this video, we will study the concept of similarity. Now, given two triangles, we say that the triangles are similar if the three angles of one are equal to the three angles of the other. Consider, for instance, the following two triangles. Triangle ABC on the left hand side and triangle XYZ on the right hand side. As you can see, this angle here is equal to the angle at X, the angle at B is equal to the angle at Y, and the angle at C is equal to the angle at Z. Right? So although these two triangles are not congruent because they don't have the corresponding equal side, they are similar because the three angles of one are equal to the three angles of the other. So the notation that we use here will say that the triangle, so we'll say that triangle ABC is similar to triangle XYZ, and of course order matters when we are enumerating the order in which the vertices of the triangle appear, and we write that triangle ABC, this is here, stands for similar to triangle XYZ. Again, order does matter when you are listing the order in which the vertices of two similar triangles are appearing. Okay, one needs to be very careful because this definition of similar triangles does not extend to other type of polygons. So for example, consider the on the left hand side we have a rectangle ABCD, and on the right hand side we have a square XYZW. Why, the four angles of one are clearly equal to the four angles of the other. They're both equal to, they all have angles of 90 degrees. However, it is clear that a rectangle is not similar to a square, right? So this concept of similarity does not extend from triangles to other polygons. So for triangle, it's actually not even necessary to check if all three pairs of angles are equal to each other. The idea here is that you can use the fact that the sum of the angles of a triangle is equal to 180 degrees to show that if two angles of one triangle are equal to the two corresponding angles of another triangle, then automatically you can conclude that all of the angles are equal. So this theorem says that if you're given triangles ABC and XYZ, let us suppose that angle at A is equal to angle at X and angle at B is equal to angle at Y. Right? So suppose this is triangle ABC, and let's say here I have triangle XYZ, and we know that the angle at A is equal to the angle at X, and we know that the angle at B is equal to the angle of at Y. So since angle at C must be equal to 180 degrees minus angle at A minus angle at B, and since angle at Z must be equal to 180 degrees minus angle at X minus angle at Y, then this is equal to 180 degrees minus angle at A minus angle at B, because angle at X is equal to angle at A and angle at Y is equal to angle at B. So this is equal to angle at C. So thus we have that angle at A is equal to angle at X, angle at B is equal to angle at Y, and angle at C is equal to angle at Z. Consequently, we can then say that triangle ABC is similar to triangle XYZ. Our next result states that if triangle ABC is similar to triangle XYZ, then the length of the corresponding sides of these triangles must be proportional. So as an illustration, let's consider two triangles here. So this is A, B, C, and I have triangle X, Y, Z, and we know that triangle ABC is similar to triangle X, Y, Z. So then the idea is that there exists a constant, let's call it lambda, which the author of your textbook called a scale factor, such that the length measurement of the segment AB is going to be equal to lambda times the measurement of XY. And if you take the measurement of BC, it's going to be again lambda, the same lambda, times the measurement of YZ. You can then guess also that AC is going to be lambda scaling XZ. So you can think of this as maybe some kind of magnifying glass, right? So if you have a magnifying glass which is scaling every shape that you're getting by a factor of lambda, and then you view the triangle ABC through the lens of your magnifying glass, then what you're going to see is a scale version of ABC, which will be essentially congruent to the triangle XYZ. So it essentially just blows up or shrinks a shape by a certain factor, and this factor is constant, and it's called the scalar factor. To prove our theorem, we will need an intermediate result. We'll need to be able to call upon the following result, which states the following. Let U and V be points on sides AB and AC of some triangle ABC. If then the line UV is parallel to the line BC if and only if the ratio AU over AB is equal to that of AV over AC. Now let alpha be UB over AB. So this will be UB over AB. And then we let beta be VC, which will be this, over AC. Then if we consider AU, clearly AU will be AB minus UB. However, UB is alpha times AB. Therefore, AU will be AB minus alpha times AB. And then we can factor AB out to get 1 minus alpha times. Similarly, we see that AV is going to be equal to AC minus VC. But if we consider this ratio here, beta, which is VC over AC, then VC is beta times AC. Therefore, AV will be AC minus B times AC, and then we can factor AC out to get 1 minus beta times AC. Now, if we consider star here, and then maybe call this one double star, and we divide star by AB, we get the ratio AU over AB is equal to 1 minus alpha. And if we take double star and we divide each side of double star by AC, we get AV over AC is equal to 1 minus beta. Now note that AU over AB is equal to AV over AC if and only if alpha is equal to beta, because one is equal to 1 minus alpha and the other is equal to 1 minus beta, right? So we can really reformulate the problem as follows. So here is a reformulation of our lemma. Alpha is equal to beta if and only if UV is parallel to BC. Now, in our triangle ABC, we're going to draw the line UC, and then we'll consider the following two triangles. So we consider triangle UBC and triangle AB and C. All right. So, moreover, regard AB as a base for triangle ABC and UB as a base for triangle UBC. Now, the area of ABC is going to be, again, base times height over 2, right? So that will be AB times some height, which is unclear. We don't know what the height is, but that's okay, over 2. And then the area of UBC is going to be UB times the same height over 2. Now, if we take the ratio of area of UBC over the ratio of area of ABC, we'll get UB times height over 2 times the reciprocal of this quantity, which will then be 2 over AB times height. Then we can cancel the heights, and then we can cancel the 2, and we get UB over AB. Okay, now we'll consider triangle BVC and triangle ABC with base VC and AC respectively. Now, the area of BVC is going to be base, which is VC times some height, call it H prime, over 2. And the area of ABC is going to be equal to AC times some height, H prime the same height, over 2. And the ratio area of BVC over that of ABC will be the product VC H prime over 2 times 2 over AC times H prime, which is VC over AC. Now, in summary, we have shown the following. We have shown that, well, this is equal to alpha, remember? Alpha is beta. This will be equal to beta, which is VC over AC. And we have shown that the area of UBC over the area of ABC is equal to UB over AB, which is equal to alpha. to summarize again, we have shown that the area of the triangle BUC, let me draw it here. So this is A, B, C, and then this is U, V. So BUC is this. We've shown that the area of BUC is alpha times the area of ABC. And we have also shown that the area of BVC, which is this triangle here, is beta times the area of ABC. So it is clear that alpha is equal to beta if and only if the area of BUC is equal to the area of BVC. So we really need to show that this equality of area holds if and only if UV is equal to BC. So we are reformulating again the problem into another biconditional statement. And this new biconditional statement, so far we have shown that the problem as stated is equivalent to showing that the area of BUC, so let me write this down here. So our aim is to show that the area of BUC is equal to the area of BVC if and only if UV is parallel to line BC. Now observe that the triangle UBC and triangle BVC have the same base BC. As such, they have the same area if and only if the heights corresponding to the base BC, which here UE and VF respectively, are equal. And we can again reformulate the problem into the following. We need to show that UV is parallel to BC if and only if UE is equal to VF. Observe that UE is perpendicular to BC and VF is perpendicular to BC as well. Thus, UE is parallel to VF. Now, next, we'll consider the quadrilateral UVFE. So inside this quadrilateral, we see that the side UE is parallel to the side VF, and since UE is equal, so let's assume for now, assume that UE is equal to VF, since UE is parallel to VF, then UVFE is a parallelogram and we can conclude that UV is indeed parallel to EF. For the converse, assume that UV is parallel to EF. Then we already know, since UE is parallel to VF, then UVEF is a parallelogram, by definition, and consequently UE must be equal to VF. Okay, so we have indeed just shown that UE is equal to VF if and only if UV is parallel to EF. And remember that we have reformulated our problem to be equivalent to that biconditional statement. So having established that biconditional statement, then we can track all the way back to our original statement to claim that the proof is indeed complete. Let us now come back to our original objective, which is to establish that if triangle ABC is similar to triangle XYZ, then the corresponding side of these two triangles must be proportional. We'll break the proof down into cases. In the first case, assume that AB is equal to XY. Then, so this is equal to that. By assumption, since the two triangles are similar, then we know that this angle must be equal to that angle, and this angle must be equal to that angle. So by ASA, triangle ABC must actually be congruent to triangle XYZ, and in that case AB over XY of course will be equal to 1, and AC over XZ will also be equal to BC over YZ, which will also be equal to 1, and will be done. For the second case, let us assume now that XY is not equal to AB, and without loss of generality, let us assume that actually XY is strictly smaller than AB. Okay. Now we will choose a point U on side AB of the triangle ABC, so that AU is equal to XY. So I'll choose a point here, U, on AB, so that if you measure the distance xy, it will be equal to the measurement of the segment line AU. Now we will draw next. We draw UV parallel to BC, where V lies on side AC. So we draw UV this way. Okay. Now, since UV is parallel to BC, since UV is parallel to BC, let's consider the triangle, the angle AUV. AUV is this angle here, right? So you can see that angle AUV is equal to angle at B, because you can regard AB as a transversal of the parallel line BC and UV. So these angles are the same. And by assumption, we know that angle at B is equal to angle at Y. The second equality is due to the fact that ABC is similar to triangle XY Z. Now let's consider the triangle AVU and the triangle ACB. So moreover, the angle AVU is equal to angle at C, which is equal to angle at Z. So let me actually, so we have this here, and then we have that. Okay, all right. Now, so we have, if I were to summarize what we have, so I'm going to compare, I'm going to pay attention to the following triangles. So we will consider, if we consider triangle X, Y, Z and triangle AUV, we see that XY is equal to AU, angle at Y is equal to angle at U, angle at Z is equal to angle at V. So by SAA, the triangle XYZ is actually congruent to the triangle AUV. So since these two triangles are congruent to each other, we can now actually say that AV is equal to the measurement of the segment line XZ. Now, since UV is parallel to BC, so this is UV and BC, then we know that AU over AB is equal to AV over AC, and since AU is equal to XY and AV is equal to XZ, we can then conclude that XY over AB is going to be equal to XZ over AC. And this brings us to the end of our theorem. All right, so let's consider the following corollary. Let U and V be midpoints on sides AB and AC respectively in triangle ABC. Then first, UV must be parallel to BC, and UV must be half of BC. So notice that if we consider the ratio AU over AB, that should be equal to 1/2, and the ratio AV over AC must also be 1/2. Thus, AU over AB must be equal to AV over AC, and by the previous lemma, UV must be parallel to BC. Okay. Now, also observe that since now UV is parallel to BC, we can regard AB as a transversal for these parallel lines. So these angles will be the same. So then the point here is that triangle AUV is similar to triangle ABC, and UV over BC must then be equal to AU over AB according to the theorem which we just proved, and that's equal to 1/2. So solving the equation UV over BC is equal to 1/2 for UV gives that UB is half of BC. In our next result, we'll prove the following. Suppose that the sides of triangle ABC are proportional to the corresponding sides of triangle XYZ. Then we can then conclude that the triangles are indeed similar. So by assumption, we have that by assumption there exists a positive real number lambda such that AB is equal to lambda xy, BC is equal to lambda yz, and AC is equal to lambda xz. If lambda is equal to 1, then we'll get that AB must be equal to xy, BC must be equal to yz, and AC will be equal to xz. And by SSS, we can then conclude that the triangle ABC is congruent to the triangle XYZ. As such, since they are congruent, then they are similar. So let us assume next that lambda is not equal to 1. In other words, xy is not equal to AB, and without loss of generality, assume that xy is actually strictly smaller than AB. So we'll choose point U on AB so that AU is equal to xy, and we draw the line UV so that UV is parallel to BC. And we choose V as a point on AC. So we have clearly the fact that AU is equal to XY. Next, observe that the angle at U is equal to the angle at B, and the angle at V is equal to the angle at C. So so clearly they share the same angle at A. So then we can then conclude, so since angle at U is equal to angle at B, angle at V is equal to angle at C, triangle AUV is similar to triangle ABC. And next, XY is equal to lambda times AB, which is equivalent to the fact that XY over AB is equal to lambda. Now, since triangle AUV is similar to triangle ABC, we know that AU over AB will be equal to AV over AC, which will be equal to UV over BC, but AU is equal to XY, so this will then be XY over AB, which is equal to lambda. Now, XY over AB is YZ over BC, which is equal to xz over ac by assumption, since the sides of triangle ABC are proportional to those of xyz. Now, from our previous equality, we get that yz over bc is going to be uv over bc, and xz over ac will be av over ac. And the first equality gives us that yz is equal to uv. The second one tells us that xz is equal to av, and we already constructed au to be equal to xy. So far we have equality here, and this will be equal to that. So by SSS, we know now that triangle AUV is congruent to triangle XYZ. As such, angle at U must be equal to angle at Y, which is equal to angle at B. Now, angle at V must be equal to angle at Z, which is equal to angle at C. And clearly, angle at A is equal to angle at X. Consequently, the angles in ABC are equal to the three angles in XYZ. So we can conclude that triangle ABC is similar to triangle XYZ. Now, we can define two arbitrary figures to be similar if for each point in one of them there is a corresponding point in the other, so that all distances in the first figure are proportional with some scale factor lambda, which is always a strictly positive real number. Consider this polygon, for example. All right, now I will construct a version of this polygon which is similar to the original one. So we will maybe shrink this by a factor of let's say 1/3. Okay, so the polygon which is inside the smaller polygon is actually similar to the polygon which is bigger, and the constant of proportionality here, our lambda here, has been selected to be 1/3. Our next result states that if you're given two triangles A, B, C, let me draw two triangle A, B, C here, and then X, Y, Z, and assume that angle at A is equal to angle at X, and let us suppose that the ratio of the side XY and AB, let's say XY over AB, is equal to the ratio of the side XZ and AC. So if you know that the angles are equal to each other, and then the ratio of these sides is equal to the ratio of the other pair, then you can automatically conclude that the triangles are similar. The proof of this result is also in your textbook, and it's very similar to the proofs that we have seen. So because of that, I will skip presenting you the proof of this result so that we can move on to something which is a little bit more novel. Our next result says the following. Given a circle and a point P not on the circle, choose arbitrary line through P, meeting the circle at points X and Y. Then the quantity Px times Py depends only on the choice of P. In other words, the quantity Px times Py is independent of the choice of a line through P. I think some illustration is in order here. So suppose we have a circle and I have a point P and I take a line, one line passing through P, meeting the circle at X and Y, and I compute the quantity Px times Py. And now I take another line which is not the same as the first one, and then is meeting the circle at, let's say, U and V, and I compute the quantity Pu times Pv. The theorem says that these two quantities are actually equal to each other. This result is actually very remarkable because the point doesn't actually even need to be outside of the circle. If you pick a point inside the circle, then, but not on the circle, then again, Px times Py will be equal to Pu times Pv. I'm sure you cannot wait to see a proof of this result. For my proof, I will only consider the case where P is outside of the circle. The case where P is inside the circle is very identical, and I'll leave that as an exercise. All right, so I will consider the triangle UPX and triangle YVP. Let me highlight these triangles here. This triangle, and then the second one is shown here. Now observe that angle at U must be equal to angle at Y, since these are subscribed angles subtending the same arc which is here arc Vx. All right. Now, since the two triangles share angle A, by AA, the triangle PXU is similar to triangle PVY. Next, from the result that we've seen earlier, we can then say that Px over Pv is going to be equal to Pu over Py. And taking a cross product, we get Px times Py is equal to Pu times Pv. So indeed, the quantity Px, Py is independent of the choice of the line passing through P.